So this is the Chapter 7 test review sheet, and I'm just going to work out every problem so you can have some detailed solutions, and hopefully this will help you as you prepare for this test. So let's get started with number 1. We're told to simplify each expression, and this is the multiplication of two fractions. And the way we go about simplifying these is, first of all, we want to factor everything we can. This left fraction, both parts are prime, so nothing to factor there. There's really two ways of handling this. I'm going to go through factoring out -1, and that gives me k squared minus 1. And I'll come back and factor this as the difference between two squares. So I'll just go ahead and do that now. You see how this factors as k plus 1 times k minus 1. So I'll just erase this and put it as the factoring of the difference between two squares. Okay, and then this denominator factors as k minus 3 times k minus 1. Okay, and now every matching factor canceling diagonally, either direction, canceling vertically within a fraction. You just cannot cancel from numerator to numerator or denominator to denominator. So it looks like a lot of this cancels, and the only thing left is -1. And that's our answer for number 1. Okay, number 2, we're also supposed to simplify, but this is a division problem. So same rule applies. We need to factor everything that we can. We'll start with this top, this left numerator, and it has a GCF. We can factor out a 2 and get 2 times the quantity d plus 3. The denominator also factors as d plus 2 times d minus 1. And now for division, remember we always flip this second fraction and change it to multiplication. So I'm going to change it to multiply, and now I'm going to put this denominator on top in its factored form. D plus 2 times d plus 1 over this, what was the numerator, and it's prime, doesn't factor. And so now the same thing applies. We have a multiplication problem, so let's cancel common factors like d plus 3, d plus 2, and everything that doesn't cancel then becomes our answer, and you do not have to multiply this out. You can leave it in factored form. 2 times d plus 1 over d minus 1 is your answer for number 2. Okay, number 3, also simplifying, and this is division. It's just written as a complex fraction, but it means division by this denominator. So let's just come up here and show the multiplication of the inverse of this denominator. B squared minus a squared over x squared minus y squared. So now that I really do not need this bottom part any longer, we've changed this into a multiplication problem. So I'm just going to erase this so we don't have to look at it. But just remember to invert the right fraction, or in this case the bottom fraction, if it's a complex fraction. Invert and multiply. Invert just means flip it over. Okay, so we're basically back to what we were doing before. We've changed it to multiplication. And so let's factor everything we can. Can't factor this left fraction at all. But once again, I'm going to turn this around, factoring out -1, and do a squared minus b squared over x squared minus y squared. And this time I'll just show it all the way out so that you can see how I'm factoring the difference between two squares here. A plus b times a minus b. And in the denominator, it's x plus y times x minus y. And now we look to cancel like factors, matching factors, like a plus b, like x minus y. And it looks like that's all we can cancel. And so we can write our answer. If we want to go ahead and multiply -1, negative a plus b over x plus y. Or I would say it's okay if you left it as, if you didn't factor out -1 and you left it as b plus a times b minus a, you could have ended up with an answer that looks like this. Same thing, just looks different. So either one of these answers would be acceptable. They really mean the same thing. If you notice, b is positive here, b is also positive here, a is negative in both places. So whichever one of these answers you get, if you got one of them, you are correct. All right, let's move on to number 4. This is where we get into addition and subtraction. So that involves finding the lowest common denominator. And the lowest common denominator, hopefully you know how to do this. I don't really want to spend a whole lot of time finding the smallest number that both 8 and 14 will divide into evenly, and that number is 56. So what I'm doing here is I'm writing the LCD twice because I'm going to divide each of these original denominators into the LCD. Okay, so another part of our LCD will be c to the 4th and d to the 2nd. Okay, so we have our LCD. We have the lowest expression that both of these original denominators will divide into. So that's what we're going to do. We're going to divide. We'll start with 8c squared d squared, and I'm going to divide into my red LCD. And the result will be 7c squared, and the d squares will cancel. So 7c squared is the result from dividing blue into red, and now I'm going to multiply that result times this numerator, and I get 7c squared y squared. Okay, over here I'm going to do the same thing. I'm going to divide blue original denominator into the LCD, and that 14 goes into 56 4 times. The c to the 4's cancel, and d goes into d squared d times. And so I take that result and I multiply it times 3x. 4 times 3 is 12 dx. And now I put this together as one single fraction over the LCD. 56c4 d2 is my denominator, and I can't combine these. These are not like terms. I just show them in the numerator being subtracted. And that is my answer for number 4. Number 5. This time it's addition, but the process is the same. I need to find the LCD, and to find the LCD I need to factor both of these denominators. So here I'm just going to show the factored form of the given problem. Okay, so the factored form of this denominator, it factors as 2 linear binomials. We can do 4x times x plus 2 plus 1. Check that with FOIL. 4x squared plus 8 plus 1 is plus 9x plus 2. Okay, and then over here we can factor first. We can take out a GCF. Remember, you should always look for a GCF first. So you can take out a 2 as a GCF, and that gets us to x squared minus 4x minus 12. And then we can factor further as the product of 2 linear binomials. The factors of 12 that add up to -6 or -4 would be -6 and +2. All right, so my factored form, actually I'm just going to mark this out so I don't have 2 of these to look at, but it's the factored form that will help us come up with the LCD easier. So I'll go with green for my LCD. So the LCD looks like it's going to be 2 times 4x plus 1, x plus 2. Since that's already a shared or a common factor, I don't need to write it twice, and then I'll include x minus 6. Okay, that is my LCD. I'll write it down twice because I'm going to be dividing into it from each of the original denominators. 4x plus 1, x plus 2, x minus 6. Okay, let's start the division process. If you divide red denominator into green LCD, the 4x plus 1 and the x plus 2 would cancel, leaving 2 times x minus 6. Okay, the parts that do not cancel need to multiply by 2x. So let's just go ahead and multiply these together. 2x minus 12. Now we're going to multiply 2x minus 12 times 2x. Okay, 2x times 2x is 4x squared. And 2x times negative 12 is negative 24x. All right, now let's work on, I didn't bring down the 3 over here. Okay, now let's work on the other fraction. So let's divide red into the green LCD. Everything cancels, if you notice, except for 4x plus 1. 2 cancels, x plus 2 cancels, x minus 6. So whatever doesn't cancel, we need to multiply by 3. So 4x plus 1 is going to multiply by 3, and that gives us 12x plus 3. And now we combine the numerators all over our common denominator. It's 2x minus 6. And combine like terms when you can. There's only one quadratic term, 4x squared. Negative 24 plus 12 is negative 12x, and then we have the one constant, plus 3. And that is our answer. Since we can't factor any more to cancel factors within the denominator, that becomes our answer for number 5. Okay, number 6, similar problem, but subtraction. So let's get right into it. Let's get the factored form of these denominators. So GCF, we can factor out a 3, x squared plus x minus 6. And let's factor further, because the factors of negative 6 that add up to positive 1 are plus 3 and minus 2. All right, so get rid of this. And over here, let's factor this denominator. There is no GCF, but we can factor it as 2 linear binomials multiplied together. The factors of 15 will go in these second places, and we've got to make sure we come up with 11 in the middle, 11x. Now you could use the box method here, but I can pretty much see it that it's going to be plus 3. That would make 6x on the outside, and with 5 that would make 5x. 6x plus 5x is 11x, and 5 times 3 is 15. Okay, so all I've done so far is factor the denominator so that I can determine what the lowest common denominator will be, and I'll do that in green. So here's my LCD. It's going to involve 3, x plus 3. They have x plus 3 in common, so I'm just going to write it once. X minus 2 and 2x plus 5. All right, and same thing over here. And we're about ready to divide. All right, so let's take our red factored original denominator, divide into the common denominator, and do you notice everything cancels except for this 2x plus 5. So 2x plus 5 needs to multiply by 4x, and that's going to be 8x squared plus 20x. All right, over here, 2x plus 5 cancels, x plus 3 cancels. Everything cancels except for 3 times x minus 2, and that's 3x minus 6. So when you multiply 2x times 3x, that's 6x squared, and 2x times negative 6 is negative 12x. And now we're ready to put these together as one fraction over the common denominator. So we're going to combine the numerators together, combine like terms. And let's see, 8x squared minus 6x squared, that's 2x squared. And then again, be careful here with subtraction. It's 20x minus negative 12x. And that's really like addition. So that's going to be plus 32x. And I would like for you to get into the habit. It's not terrible if you stop here. Only what would be terrible is if we had an opportunity to cancel between the numerator and the denominator and we didn't take advantage of it. And you typically won't know that unless you factor. So I'm going to go ahead and factor this numerator because there is a GCF, 2x, and that would be x plus 16 all over the common denominator. So factoring did not give me any opportunity to reduce, but it's a good habit to get into because when there is an opportunity to reduce or cancel, you'll be able to take advantage of it and you won't miss points by not reducing your final answer. So that circled is the final answer for number 6. Okay, now we get to a graphing problem, and this was taken from our lesson 7.3. It's inverse variation, the graph of inverse variation function. So the way we did this in lesson 7.3, if you want to go back and review your notes, is we said that it's really the translation of a parent, and the parent in this case would be f of x equals negative 1 over x, but it's the parent that has been shifted one place to the right, so that's going to represent a vertical asymptote, x equals 1, and it's also being shifted one place up. So the original horizontal asymptote for the parent is the x-axis. Well, when we shift up, it moves it up to the line y equals 1. Okay, and similar here, the original vertical asymptote is x equals 0, or in other words, the y-axis, but this says to shift one place to the right, and so that basically shifts our vertical asymptote one place to the right. So remember, where these two lines cross each other is our new origin. And all we have to do is make a table of values for the parent and plot from this new origin. Okay, obviously we can't use 0, but we can use numbers like 1. If x is 1, we get an output of negative 1. We can do 2. That gives us output negative 1/2. Input 1/2. You get output negative 2. Okay, so let's go ahead and plot these points, and then we'll work on the other branch. Remember, these inverse variation functions always involve two parts. We call them branches. And so let me put my vertical asymptote back. All right, so here we are plotting these points from this red dot called our new origin. So 1, negative 1 would be here, 2, negative 1/2, and 1/2, negative 2. And this represents part of our graph. And then the other branch we will obtain by just choosing the opposites of these numbers. So I'm just going to list them out separately. And plugging these in. So if I plug in negative 1, I get positive 1. Negative 2 gives me positive 1/2, and negative 1/2 gives me positive 2. Okay, so let's plot these to get the other branch. Again, going back to my new origin, negative 1, positive 1, negative 2, positive 1/2, negative 1/2, positive 2, and here is my other branch. Okay, and that should take care. Let's put this horizontal asymptote back. It should take care of problem number 7, a inverse variation function. Your book calls them reciprocal functions, but you probably have heard a lot that inverse and reciprocal are interchangeable terms. Okay, so here we are with number 8, and this is actually current stuff for us because we've changed the order around a little bit of the lessons. This is lesson 7.4. So let's go ahead and graph this rational function. The first thing you should always do, if you can, is come up with the factored form. That makes these steps that we're going to go through, if factoring is possible, in many cases it helps these steps go by a lot easier and quicker. So there is a way to factor this denominator. We can factor it as x minus 2 times x minus 1. All right, and the great thing about that is that we're able to cancel or reduce because we have x minus 2's as a common factor. And so this becomes 1 over x minus 1, which looks a lot like what we just did. The inverse variation function is very similar. Okay, but let's go through our steps because you never know on the test what kind of graph you're going to end up with. But what we're doing, this process is always true. You should always factor. Then you work your way into finding zeros or x-intercepts. And that involves letting the numerator equal 0 and solving. Well, we don't have a variable in the numerator any longer since we canceled, so we do not have any x-intercepts. This graph is never going to touch the x-axis. Okay, so now we're going to find asymptotes. Do we have, first of all, a vertical asymptote? Well, let's see. We're going to have a vertical asymptote after canceling. We're only going to have a vertical asymptote here at x equals 1. So let's just go ahead and draw that. Okay. Are we going to have a horizontal asymptote? Remember, the horizontal asymptote will show up. There's two different cases where it will show up. And here we have the degree of the numerator is smaller than the degree of the denominator. So we will have a horizontal asymptote, and when this happens, it's always going to be the line y equals 0. Or that's another way of saying the x-axis. So I'm going to go ahead and draw on top of it just for emphasis. Okay, so we have a horizontal, we have a vertical. Do we have an oblique? We do not have an oblique because the numerator degree is not larger, and it's got to be larger by 1, and there also cannot be any common factors, so there obviously will not be an oblique asymptote. And now let's take a look at holes. Is there a hole in the graph? There will be a hole in the graph if you have a number that makes both numerator and denominator 0. That's what happens here. X equals 2. If x is 2, then not only will the denominator become 0, but also the numerator. So let's not forget to go back when we have something graphed, and we need to place a hole in the graph where x equals 2. Okay, and now you can go to your table, and let's get some inputs and outputs. We're going to see what happens on either side of x equals 1. So let's input 2. If I input 2, we'll just put our function here that we're going to be inputting into. After we cancel, see, we're only going to input in place of 1x instead of 3. So it's going to be pretty nice. So if I input 2, I get output 1. So I'm going to go ahead and draw this, even though I know that eventually I'm going to put a hole at this place, but I'm going to wait until I get something drawn. Okay, and then what about input 3? If I input 3, 1 over 3 minus 1, that's a half. Do 3, a half. So I'm pretty much confident that this graph is going to pass through these points, and it has to follow along this horizontal asymptote forever. I bet if I do 1.5 as an input, I'm going to get something up here above y equals 1. So let's see, 1 over 1.5 minus 1, that's 1 over a half, which is 2. So sure enough, if I do 1.5, I get output 2. So that gives me good information about how this graph is behaving. So the right side of the vertical asymptote looks like this. And now let's work on the left side. So we're going to choose numbers to the left of x equals 1. We'll start with 0. Okay, if we input 0, we get an output of negative 1. 0, negative 1. If I input negative 1, let's keep on going with our table here. If I input negative 1, I get output negative 1/2. And it looks like it's doing pretty much the same thing down in this area. And if I input negative 1/2, I'm going to get output negative 2. And so this ends up being the other part of the graph. Okay, now for the hole. There's supposed to be a hole in this graph where x is negative 2, or positive 2, sorry. So what I'm going to do is go to where x is 2 on the graph, which is that point right there. And I'm going to erase a little space there because really my graph should not go through this point. It's going to jump over that point and then continue on to the other points. But we cannot do an input of 2, or else if we do, we're going to get a division by 0. So that graph is complete. We are finished with number 8. Let's move on to number 9. Number 9 is an inverse variation problem, and this is from lesson 7.5. So remember, inverse variation, we're told x and y vary inversely. Inverse variation looks like this in equation form, and this number that we call k can be found just by multiplying x and y together. So that's really the purpose of these two numbers. When x is 14 and y is negative 3, that will help us figure out what this constant, we call the constant of variation, what that number actually is. So for letter A, write a function for the inverse variation. So I'm going to use this model, this template, and I'm going to put negative 3 in for y, and I'm going to put 14 in for x, and I'm going to solve for k, multiplying these together. K is negative 42. So letter A, the function for this particular inverse variation is y equals negative 42 over x. That's the answer for part A. Now part B will require using this function. It's pretty easy. Find y in this function if you let x be negative 7. All right, and negative 42 divided by negative 7 is positive 6. So there's your 9A and B answers. Okay, number 10 is what we call a combined variation because it's got direct, remember direct variation is multiplication by k, and inverse variation, as we just saw, is division into k. Well, this employs both of them. Z varies directly with x. Let's just show that part. Z varies directly with x and inversely with y. So every time you see directly, you're multiplying times k, and when you see inversely, you're dividing into k. Okay, so these numbers are going to be helpful to help us find out what k actually is. So let's plug in. So we're doing part A. Write the function that models this relationship. So let's plug in 42 for z, 2 for x, and 3 for y. Okay, now let's solve for k. We'll multiply 42 times 3, that's 126. And if you divide by 2, that means k is 63. So here is my letter A answer. The function that models this relationship will be z equals 63x over y. Okay, and now let's answer part B. Using this function that we just came up with, let's find out what z is if we plug in 3 for x, 63 times 3, and 6 for y. All right, so we can we want to go ahead and do a little reducing first. Since these are factors, remember you can cancel factors. You can make this 1 and this 2. Then now we can multiply both sides by 2. 2z is 63. So z is going to be 31.5. So that's your part B answer. Okay, so we got parts A and B for number 10. And we're good to go. Let's move on. Oh, another, this is application, real life application of inverse variation. It's a nice little problem. So we're told that the length of a violin string varies inversely as the frequency of its vibrations. So I'm just going to use L for length, varies inversely. Remember, that's division. And I'm going to use V for vibrations. Okay, length varies inversely with the frequency of its vibrations. Okay, so what we're about to be given is going to help us find out what this actual number called K is. A violin string 14 inches long, that's length, vibrates at a frequency of 450 cycles per second. That's V. All right, and so we'll grab our calculator and we're going to multiply both sides of this equation by 450. So 450 times 14, that's 6,300 equals K. So now we know a specific model that represents this, this inverse variation relationship. L is equal to 6,300 divided by V. Okay, so we're going to use this to get our final answer. Find the frequency, okay, the number of vibrations of a 12-inch violin string. Okay, so they've given us L, it's 12. We've got to solve for V, frequency of the vibrations. Okay, so 12 equals 6,300 V, multiplied by V on both sides. 12V is 6,300. And now we need to divide by 12 on both sides, and we'll have our answer. Vibration frequency will be, let's see, 6,300 divided by 12. That's 525, and the units they're using are cycles per second. And that is our answer. It vibrates at 525 cycles per second for a violin string that's 14 inches long, or 12 inches long. Okay, very good. Let's go on to number 12. Now we're going to be solving some rational equations. And to do this, we need to factor the denominators if possible. And the only one of these denominators that factors is the one on the right. So let's show the factored form. 2x times x, and then we'll have the factors of -3 placed in the proper positioning so that we come up with -1 in the middle. So this should be +1 and -3. 2x squared plus 2 minus 3x is -1x minus 3. Okay, since we have shown the factored form, I'm not going to look at this one any longer. And the reason for factoring everything is so we can come up with the LCD and multiply by the LCD on both sides of the equation. So the LCD is 2x minus 3 times x plus 1. And I'm just going to show that that's going to be multiplied on both sides in order to clear the denominators and turn this rational equation into a non-fraction equation. All right, so the 2x minus 3's cancel. X plus 1 times 4 is 4x, x plus 1 times 4 is 4x plus 4. All right, now I divide x plus 1, and the x plus 1's cancel. 2x minus 3 times x is 2x squared minus 3x. Over here, everything cancels, becomes 1. Anything divided by itself is 1, and 1 times negative 8x. Okay, so it looks like we're headed toward a quadratic equation. So let's put it in standard form and combine like terms. 4 minus 3x is 1x. And, I've got to add 8x to both sides, so x plus 8x is 9x plus 4 equals 0. Okay, so we're all good to go. And let's see if we can factor this. 2x times x, and we need the factors of 4, so that will be 4 and 1. Let's check that with FOIL. We get 8x plus 1x is 9x. 1 times 4 is 4. We're good. And so now we solve, and we get x equals negative 1/2. X equals negative 4. We want to double check and make sure that neither of these creates 0 in a denominator anywhere, and they don't. And so those are my solutions. That's your answer for number 12. Okay, moving on to number 13. This is a rational inequality. And the first thing we want to do is note the numbers that x is not going to be allowed to be. We can't divide by 0. And so we're going to say, first of all, that x cannot be 0. And that's going to be one of the numbers on a number line that we will create and test around. But we need to find other numbers by solving this as though it were an equation. Okay, we're going to pretend for just a minute that we're solving this equation. We need the LCD. So let's see if we can figure out what is the smallest term that we can divide into evenly. Looks like that's going to be 30x. So when I divide 2x into 30x, I get 15. 15 times 1 is 15. If I divide 5x into 30x, I get 6. 6 times 4 is 24. And over here, 3 into 30x is 10x times 1 is 10x. 15 minus 24 is negative 9. Dividing by 10 on both sides, I get negative 9/10 is x. Okay, so there are two numbers that I'm going to have on a number line. 0 and negative 9/10. And these two numbers basically create three areas. I need to grab numbers out of each of those three areas to test. So I'm going to choose negative 1. Let's see, negative 1/2 and positive 1. And we're going to go back up to the original inequality and see if these numbers make this true or false. So when we plug negative 1 in, let's see, we get negative 1/2 minus negative 4/5. Is that greater than positive 1/3? And let me erase my x can't be 0 here. So negative 1/2 plus 4/5. We want to know if that's greater than 1/3. And if we change to a common denominator, this would be in tenths. Negative 5/10. And this in tenths would be 8/10. So we got 3/10. Is that greater than 1/3? And if you want to do this in 30ths, 9/30ths, 10/30ths, no. 9 is not greater than 10, so these do not work. Okay, so let's test -1/2. Okay, so here we go. 1 over 2 times -1/2, that's just going to be -1. And then 4 over 5 times -1/2. Is that greater than 1/3? -1. Let's just show this. 5 times -1/2 is -5/2. So let me show it like this. 4 divided by -5/2 is the same thing as 4 times -2/5. So it's going to be 1 minus -8/5. And we want to know if that's greater than 1/3. All right, so -1 plus 8/5. -5/5 plus 8/5 is 3/5. And is that greater than 1/3? If you're not sure, you can put these in terms of 15th denominators. This would be 9. This would be 5. And yes, when I do -1/2, I get a true statement. Okay, now let's try 1. And we will have all of our testing done, and then we'll be ready to write an inequality statement. So if we input 1, we get 1/2 minus 4/5. Is that greater than 1/3? We can just go ahead and do, if you want to go ahead and do 30s all the way across, denominator 30. This is 15. 5 into 30 is 6. This is 24. And this is 10. So -9/30 is not greater than 10/30. So these do not work. So my final answer, after all that work, is all the numbers in between -9/10 and 0. That is my final answer for number 13. Okay, number 14. This is a review problem going back to chapter 5. And it's a transformation of a parent. And I want you to make sure you're familiar with these parent functions. So here's what the parent function f of x equals the square root of x looks like. It starts at the origin. We include the point 1, 1, 4, 2, 9, 3. Of course, there's many other points, but we just typically use those as a reference. The parent looks like this. It's that curved ray shape that has an endpoint at the origin. All right, but what this is a transformation, because we're going to take this parent and we're going to multiply all of the y values of the parent by -2. Okay, so I'm just going to do that a step at a time. So if I do all of the y values by -2, that means that the origin is not going to move. Okay, 0 times -2 is still 0. All right, this is a shift horizontally of 2 to the right. All right, so I've multiplied the y of this point by -2, didn't change. I'm going to go right 2, and then I'm going to do the vertical move of up 1. Okay, so this is right 2, up 1. This is multiplying the y of each of these 4 points by -2 to cause it to flip over. And so -2 doesn't change, right 2, up 1, and that origin point has been relocated. All right, let's take a look at this one. It has a y coordinate of +1, but when I multiply by -2, that makes it become y is -2. Then I'm going to travel right 2, up 1, and now this point has been relocated. All right, let's take a look at this one. It has a y coordinate of 2, but when you multiply by -2, it makes -4. So here I am at -4. Now I'm going to do the right 2, up 1, and that point has been relocated. Okay, y coordinate 3 times 2 makes y coordinate -6. And I'm going to go right 2, up 1. And this is the graph. Oh, just missed that one big time. See if I can get it this time. Pretty close. Okay, so I just want to refresh your memory a little bit on how to do these square root functions. What's the parent look like? And then how do we transform the parent? All right, now we're back to some log equations. And there's really two different ways you can go about this particular problem. I'm going to go about it so that you have to remember the property, the product property, which says that two logs of the same base that are being added can be joined together as one single log using that base using multiplication. All right, so I've turned two different logs into one log. And now I'm going to turn this log equation into an exponential equation. Oh, so the way that works is you take the base, and you remember that logarithms always equal exponents, because that's what they are. Logarithms are exponents. So 3 to the third power is going to be equal to 3 times a squared plus 3. 3 to the third power is 27. Dividing by 3 on both sides. Divided by 3 on both sides gives me 9 equals a squared plus 3. Subtracting 3 gives me a squared. And now square root of both sides gives me plus minus the square root of 6 is equal to a. And that are really two answers for number 15. Okay, so I just want you to remember, we'll keep drilling the properties of logarithms. This is an illustration of the product property. And it's also important that you can turn log equations into exponential equations in order to solve them. Okay, here's another log equation. And so this time we're going to use the quotient property. Two logs of the same base that are being subtracted. You can put those together as a single log using division. Okay, now that I have single log form, I'm going to turn this log equation into an exponential equation. 4 to the first power is equal to this fraction, 2y plus 2 over y minus 2. I'm going to multiply both sides by y minus 2, so 4 times y minus 2 is 4y minus 8. And I'm solving for y, so I'm going to subtract 2y from both sides. I'm going to add 8 to both sides, divide by 2, and I get my solution is y equals 5. Very good. We're moving right along. Okay, now this is an exponential equation. So we looked at a couple of log equations. Now let's take a look at how exponential equations are solved. So I'm going to turn this into a log equation. Anytime I'm trying to solve an exponential equation, it needs to be converted into a log. Log base 5 of 9. Remember, logarithms always have to equal exponents. So the exponent is x plus 2, so that's what I'm letting the log equal. Now, this is an occasion where you have to use that change of base formula. Because when you hit the log button in your calculator, if you just hit it one time, it's assuming base 10. Well, this is base 5. So to get around that, we do the change of base formula, which is log 9, log of the top number, divided by log 5. So I just grab my calculator, and in your calculator, if you hit the log button, put 9, close the parentheses, divided by log button again, put 5, close parentheses, you should see this decimal. So we're supposed to round to 10 thousandths, that's 4 decimal places, so I'm going to say that's 1.3652. 1.3652 equals x plus 2. And to solve for x, we need to subtract 2 from both sides. And if you want to just leave that in your calculator and do minus 2, and that's negative 0.6348. And that is our answer, negative 0.6348. That's our answer for number 17. Number 18 works similarly, but it's an inequality, of course. So we need to change this into log form. The base will be 3 of 4 to the x. And I'm going to turn this around so that it's still pointing at the exponent. Remember, logarithms and exponents, in this case, they need to be on opposite sides of the inequality. Okay, and once again, we're going to use the power property this time. We haven't looked at that yet, to turn this into this. Okay, so let's go back to our change of base formula. We're going to do in our calculator log 4 divided by log 3 and see what that decimal is. And it looks like it's 1.2619. 1.2619x greater than or equal to x minus 1. Okay, so to solve for x, I need to get x's on the same side. So I'm going to subtract 1x from both sides. Okay, so going back to my calculator, I've already got this number in here. So I'm just going to do minus 1. So that's 0.2619x is greater than or equal to negative 1. And now I need to divide both sides by 0.2619. So that will be negative 1 divided by 0.2619. Negative 1 divided by 0.2619, and it looks like it's negative 3.8183. Okay, and that's our answer for number 18. Last two. All right, these are natural. This is a natural log equation. This is an exponential equation that's base e, so it needs to be changed over into a natural log equation. So natural log equations need to turn into this. E to the x equations need to be turned into this. So first of all, before I can make any change in this, change it to exponential form, I need to get rid of any number that's being multiplied times the log. So that's easy enough. We'll just divide by 5 on both sides. And now I need to change this natural log equation into an exponential equation. And remember, natural logs have base e. So when I change this to an exponential equation, it's going to say e to the 8/5 power equals 6x. All right, so we need to grab our calculator again. And this time you're going to hit the e to the x button. And that exponent that you're going to put in parentheses will be 8/5. So in your calculator, should look something like this. You're going to raise e to the 8/5 power and then hit equals. Okay, so e to the 8/5 power is 4.9530. And now we'll get our solution, dividing that decimal by 6. And we'll get our answer. Some calculator. Okay. 0.8255. 0.8255. And that's our answer for 19. And now number 20. We need to isolate e to the x first. That's an important first move. 2 steps will accomplish that. Add 3 to both sides. Divide by 6 on both sides. And you can reduce this if you like. Really doesn't matter. You're going to be using your calculator for the most part anyway. So now that we've isolated e to the x, we're ready to change this into a natural log. So you notice how it works. Natural log equations get converted to e to the power. E to the power get converted to natural logs. That's how you solve these. So natural log 38/6 equals our answer, x. So using our calculator, hitting the natural log button, ln, putting in parentheses 38/6 equals, and you should get 1.8458 as your final answer. And that should do it for this review sheet for Chapter 7, plus a little bit of review of previous material. And work hard on it, prepare well for your test. Let me know if I can help.